Welcome back. In the last video we have seen how to solve a wave equation in a semi-infinite domain, that is 0 to infinity, with the when the boundary condition is fixed, that is u at 0 t is 0. Okay. So, with the general initial data we have solved, we actually constructed and the solution, and we have seen a new approach. So, in a different approach, not by extending as on a full domain and then make use of the D'Alembert solution, and a new approach without making use of the D'Alembert solution, we have seen how to construct a solution in the semi-infinite domain. Today we will see, in this video we will see how to construct the similar thing when the boundary condition is different, that is free edge boundary condition. So, let us write the problem. So, utt minus c square uxx is 0. This is your wave equation for x positive and t positive, the semi-infinite domain. Now, initial data is as usual, ux0 is fx, ut at x equal to 0 is gx is given. This is your initial data, okay. And the boundary data is, that is you have only one boundary at 0, x equal to 0, and this is infinity, okay. So, your this is t at x equal to 0, that means on this boundary you are giving it is free edge, that means the slope of that is 0 at x equal to 0. So, ux at 0 t equal to 0 for all times, that is the meaning, okay. So, ux 0 t is 0 is your boundary condition again. So, we do not really extend it as a even function here like we did earlier. So, what we do is we take the general solution of the wave equation that we already know. The general solution of wave equation is uxt is let us say some c1 of x minus ct plus c2 of x plus ct. So, where c1 and c2 are arbitrary, c1 c2 are arbitrary functions, and if you apply the initial data, you finally see that like earlier you can actually find what is your c1x and what is your c2x, okay. So, I will just pick it up from earlier what we had derived after applying initial data. So, by doing this you see one is c1 you will get minus k by 2. So, k is an arbitrary constant. So, you see that half fx plus 1 by 2 c integral x naught to x g of s ds minus k by 2 as your c1x, okay. c1x you have this where k is arbitrary constant. K is actually c1 at x naught minus c2 at x naught. So, that is some arbitrary constant. So, another one is c2 is half fx plus 1 by 2 c x naught to x g of s ds plus k by 2. This is how you will get, okay. This is what we have seen even in the earlier example. So, once you use this, and you can see that the general solution is this. Now, again x minus ct can be negative for larger times. So, you need c1 a negative function, that I can get it from the boundary condition, okay. So, that boundary condition, so you can see that where k is actually, so what is k? K is c2 at x naught minus c1, c2 at x naught minus c1 at x naught. Now, let me apply the boundary condition. Boundary condition will get you what is your c1 for the negative values. So, ux, that is ux at 0 t equal to 0, the boundary condition implies c1 minus ct c1 dash, okay. So, how do I do this one? This is c1, this function you have to differentiate with respect to, this is like dc1 by dx minus ct into dx minus ct divided by dx, that is my dc1 by dou c1 by dou x, okay. You can say dou, both are, all are dou, these are because two functions are involved, okay. This is what is my dou u by dou x. The first term I did, that is what I get. Now you see that dou C2 by dou x minus Ct and into dou of x plus Ct divided by dou x, this is plus. Okay. Now this whole thing you are putting at x equal to 0, okay, this whole thing at x equal to 0. Okay, this is equal to 0. So this is exactly whatever is the left hand side is my ux at 0 t. So this gives me C1 dash of minus Ct. Okay. When you put x equal to 0, d C1 by d of minus Ct, okay, of C1, C1 of minus Ct, okay, C1 of x minus Ct when you put x equal to 0 minus Ct. So this is exactly C1 dash of minus Ct plus C2 dash of Ct equal to 0. This is what you will get. Now if you integrate, if you simply integrate, how do I integrate? Like earlier, if you simply integrate from, so see that t is positive, so implies Ct is also positive. Okay. You can consider x naught equal to 0. This is you have a domain is from 0 to infinity. Okay. So you can think of, so this is only taking positive values. Okay. C1 of minus Ct, Ct is positive. Okay. This is that you can think of Ct as L. So this is your L is always positive including 0. Okay. So you can integrate this. So first you write this C1 dash of minus x plus C2 dash of plus x equal to 0. In a notation I am simply replacing x equal to where x is Ct, which is because T is positive, this x is also positive. Okay. So that is what I mean. So because it is positive, so x is positive, you can integrate this from x naught to x. That is now I can take x naught, I can fix my x naught as 0. Okay. So I can fix my x naught as 0, 0 to x if I differentiate, I can integrate C1 dash of minus x plus C2 dash of x into dx, okay, equal to 0, right side integration anyway 0. Okay. So you have, what you have is, this is integral 0 to x dds of or ddx of, this is C2 of x minus C1 of minus x. You differentiate, this is exactly you get the integrand. C2 dash I have minus plus C1 dash of x. Okay. You differentiate this C1 of minus x, you get minus of C1 dash of minus x. So minus plus you will have this. This is dx equal to 0. Now this is at x, that is C2x minus C1 of minus x equal to minus of at 0. So that is C2 of 0 minus C1 of minus x minus 0, that is 0. Okay. This is what is my this one. So now what is this one? This is equal to, now when you are applying the initial conditions, you integrate it from x naught to x. There also you have a domain, your domain is from 0 to infinity, x is from 0 to infinity. You can choose your x naught as 0. If you do that, your k will be simply C2 at 0 minus C1 at 0. So C2 is 0, C minus C1 is nothing but your k, same k. So this will give me C1 at minus x, x is positive, okay. This is equal to C2x minus k. This is for x positive, okay. So this means C1 x equal to C2 of minus x minus k for x negative. So this is what I got. So I now find what I want C1 function for the negative values. I know what is my C2, C2 is this, I make use of this to write for the negative values. Okay. So, what I want is C1 at x minus Ct. So, this is where when I will get it, this is when I know that when I require u of xt for x is between 0 to Ct, that is where C1 of x minus Ct in the general solution, you have a general solution here. Okay. So, that can be negative. So, that negative function is actually equal to, in this when x is between 0 to Ct, C1 of x minus Ct, x minus Ct is negative like here, and this is nothing but C2 of minus x. What is C2? C2 is half fx, that is half f of minus x. F of minus x means that is C2x, C2x is minus, x is now x minus Ct. So, you have Ct minus x. Okay. F and then plus 1 by 2 c integral 0 to x gs ds. 0 to x is, you have to write minus x, that is C2 minus x, x minus Ct minus of that is Ct minus x. You have gs ds. Okay. And this one if you add with C2, C2 of x plus Ct, C2 of x plus Ct is simply half of f of x plus Ct plus 1 by 2 c integral 0 to x plus Ct g of s ds. So, this sum is nothing but, so this is what is x minus Ct. So, this is from 0 less than x less than Ct. Okay. So, for the same x is between 0 to less than Ct, your C2 is anyway whatever may be x plus Ct is anyway still positive. So, you have to use the same Ct. So, this implies u of xt when x is between 0 to Ct, you have this summation, that summation is half of f of Ct minus x plus f of x plus Ct, and now this one you can simply add together, and of course C1 I have a minus k. Okay. So, I missed something here. So, you have a minus k, right. So, you have a minus k here, and here C2 is plus k by, so sorry C1. So, you are replacing C2. So, that is plus k by 2, that is plus k by 2. What is that? Missing something. So, C2. So, this is, you have what you have written is C1 this equal to C2 of minus x minus k, and what you have is, what I missed is C2 is plus k by 2 is missing. So, plus k by 2 is also there. Okay. So, you have a C2 of minus k, you have plus k by 2, and you have a minus k here. Okay. So, together this is minus k by 2, and C2 is, you have here plus k by 2. And now, if you add these two gets cancelled. Okay. This is what it means. This is for x less than Ct. So, what you have is, when you add it, what you are left with is simply this into 0 to Ct minus x gs ds plus 0 to x plus Ct gs ds for this domain. What happens when x is greater than Ct? Both C1 and C2 both are positive. C1 x minus Ct x plus Ct both are positive. You simply take from here their addition. So, this k by 2 goes, we simply have usual D'Alembert solution. For x greater than Ct, what you have is simply D'Alembert solution, that is half times f of x minus Ct plus f of x plus Ct plus 1 by 2 c integral x minus Ct to x plus Ct gs ds. So, this is how you constructed your solution when your boundary condition is free edge boundary condition. Okay, at x equal to 0 the string is like a free. So, you have the slope is 0. If you want this to be a solution, if u is a solution, u of x t is a solution, is the solution because we have it is a unique solution, is the solution, then again it has to satisfy wave equation. So, f is twice differentiable, f dash, f double dash and g is g dash are continuous, exists and continuous or continuous functions. Okay. And immediately by making use of u continuity, u is continuous, gives something. Okay. U or ux or ut are continuous. If these are all continuous, in fact uxx also, uxx utt, they are all continuity, will give you finally f dash of 0 is 0 and g dash of 0 is 0. So, these are the conditions we used by extending the domain from 0 to infinity to as a even extension you have taken. So, you extended the domain to minus infinity and made use of D'Alembert solution for the full real line. So, in that case when you extend as an even function, these are satisfied automatically. So, by the initial data, and here also by just substituting this and into the, if this has to be a solution, necessarily the initial data, that is by f and g functions, should satisfy this, okay, along with this differentiability and continuity of these functions f and g. This is how you can construct your solution when the boundary data is given like this, and the boundary data is free edge. When the boundary data is one of these other edges, okay, you approach is same. You first have by apply the initial data, get your C1x and C2x. Now, because of u0t, so because x minus ct, because your x is positive, x minus ct can be negative. So, apply the boundary conditions either this or this and try to get your C1 for negative values of x, negative ordinate, okay, C1 of x when x is negative, that is what I have to find out, that you can get it from this one. Just by applying to the general solution of the wave equation, you can get that. But because when you put x equal to 0, what you are getting is C1 of minus Ct. So, obviously you are able to get C1 of minus Ct, that you call it some x. So, you have a negative values of x, you can get your function C1, and that you substitute, that you can get in terms of C2 from the boundary condition, that you make use of that, and finally you substitute into the C1 and C2, you will get your solution in this domain. That is the only thing extra, otherwise other part is simply D'Alembert solution, okay. So, this is how you can apply this approach. This is the more general approach, so that you can apply, you can even use for other boundary conditions. So, this is how so far we have seen how to solve a wave equation with the initial data in the full domain minus infinity to infinity, or a wave equation with initial data and on a semi infinite domain, that is 0 to infinity, so that you have a boundary. On the boundary you can give any boundary data, okay. So, any type of boundary data whatever is given, you can actually construct your solution in this fashion, okay. So, now let us move on to wave equation solutions. So, what are the problems we can have if you have a finite domain? So, that means consider a finite string. If you have a finite string, vibrating string, so initial data is like u, so its displacement of the string is given initially at t equal to 0, you can have u at x0 equal to fx, that is given x is between a to b. A to b is a finite string, okay. So, your finite string is string of length b minus a, that is, so let us say at x equal to a is one end and x equal to b you have other end, and other initial data is ut at x equal to 0 is g of x, that is the slope of this string is at every point is given as not slope, sorry, this is actually the vibration. So, initially your displacement of the string its velocity of the string at initial time at t equal to 0 is given as g of x, that you can show graphically. So, these are given, this is what is the initial data. A boundary data now you have to fix, because you have a boundary here a and b. So, that is u at a for all times, u at b for all times. So, you have to provide this boundary data, because you have a boundary involved here. Okay. So, because you have this boundary involved, so you have to provide this boundary data for the solution. So, that is how you make the problem well defined. Okay. So, what do I do? So, you can fix physically, you can fix your string as fixed string or allow it to be free, just like you have seen earlier. So, if you make this these two boundary conditions, you can give 0, or boundary conditions you can change it. So, you can have you can fix it, one end you fix it, one end I can fix it, other end I can simply take I can make it to be free, that is x derivative at bt equal to 0. So, this is like one end fixed, it is like fixed free, okay, fixed free, this is fixed, okay, both end fixed. Like that you can have a combination, u x at at is also 0, u x bt is also 0. So, this is like free, okay, at both the ends. So, like this you can have. So, a string is satisfying the wave equation. So, you can now write the boundary value problem, initial boundary value problem. For wave equation in the domain, in the finite domain rather, okay, in the finite domain, one dimensional wave equation in the finite domain. So, you have u x u t t minus c square u x x equal to 0, x is now not full real line, not semi infinite. So, it is simply from a to b, you have a to b and t is positive. Okay. So, these are the two, this is your domain, this is your domain. Now, give the initial data, that what you have there. So, you have u at x 0 like earlier f x, u t at x equal to 0, velocity of the string at x equal to 0. This is your initial conditions. Okay. Now, give the boundary data, that is the boundary conditions. You can give one of them. I start with this fixed string, that is u at a t equal to 0, u at b t equal to 0. So, this is the problem. Now, how do I solve? How do I find my u of x t for all t? So, this is initially you know something, boundary data you know. So, the question is how to find, how to solve, how to find the displacement of the string for all times, for all t positive and for every x everywhere in the all along the string, how do you find the displacement? This is the question. Okay. So, this is where we use we can actually use something similar arguments like earlier arguments, but let us because we have learned ordinary differential equations, we try to, and we used we have learnt Sturm Liouville theory, we try to extract a Sturm Liouville theory. Okay. So, when the spatial domain, one of the spatial domain is finites, okay, you have a t and x variables, t is positive, it is an infinite domain, but x domain is finite. Okay, you can see this. When you have such a domains, and you can actually extract Sturm Liouville problem out of this PDE by a technique called separation of variables. If you apply, if you look for solutions, so this is called separation of variable technique, method to find u x t. Okay. So, this is what we do to find this u of x t. Okay. So, separation of variables I am applying to just to find the solution of the wave equation, let us see. Okay. So, wave equation is homogeneous equation. So, you have 0 is the actually solution, because you look at the equation 0 also satisfies. If you replace u of x t is 0, if you take u of x t as 0, 0 satisfies. Okay. So, you are looking for a non-zero solution, look for, let u of x t be some x of x. I separate these variables x of x into t of t, which is non-zero, okay, as a solution of the wave equation. You look for in this form, you look for solution in this form. Okay. So, if you do that, you substitute that into this form, you substitute into the equation now. If you do that, what you get is utt, that is utt means now this is x of x is there is it is only function of x and function of t. So, what you get is x of x t double dash of t with respect to this is like d square t by dt square minus c square, that is anyway constant, and now here u x x, that is x double dash of x t of t equal to 0. So, if this is how you look for a solution, this is what it becomes. Okay. Then this implies you can write x of x double dash of x, okay, by x of x equal to, okay, so you can make it equal, you take it to the right hand side and divide with, because this is non-zero, you can divide both sides with x of x and t of t. Okay. You can simply divide because it is non-zero, that is how you are looking for solution. So, if you do that, you get this one side. Okay. If you first time, so let us do this. So, x of x t double dash of t equal to c square x dash of x t of t. You divide now both sides with x of x and t of t, because it is non-zero. Okay. T of t goes, x of x goes. So, what you are left is, I will write like this, x dash of x divided by x of x equal to t dash of t divided by c square t of t. Okay. This is what you get. So, now the variables are separated, x of x and t of t. This one side is functions of x, other side is functions of t. So, if you have two independent variables x and t, one function is same, left on one side is a function of x and other side is function of t, and x and t are independent variables, then it has to be constant. So, this is some constant, call this lambda. Okay. It has to be constant, and that is you call it lambda is a parameter. So, this implies x double dash of x minus x of x minus lambda into x of x equal to 0. Okay. This is one problem for x of x, other one is t double dash of t minus lambda c square t of t equal to 0, that is another problem for t of t. Now, we consider this one. Okay. Now, your u of x t is a product of x and t. So, apply the boundary conditions. What you have the boundary? U at a t is 0. Boundary conditions give u at a t is 0, gives, this means x of a t of t has to be 0. T of t cannot be 0. Okay. Because it is a function of t. If this is 0, then this is 0, u of this, but we know that we started with non-zero solution. So, this implies x at a equal to 0. So, you got a boundary condition, you have a boundary condition for x. This is what is your domain for x? X is between a to b. when you are separating you write like that, and here t is positive. Now for this problem you have found a boundary data x at a. Similarly, you have u at b t equal to 0 will give me x at b t t is 0. So, because t t cannot be 0, so that is x at b equal to 0. Okay. So, this is your boundary data. Boundary conditions will give you, if you apply the boundary conditions, they give you that x of a equal to 0, x of b equal to 0. This is the Sturm-Liouville problem. So, now you have extracted a Sturm-Liouville problem, Sturm-Liouville problem the system regular Sturm-Liouville system you extracted. What you have is mostly regular usual problems, but certain when you are working so in the Cartesian coordinates you always extract regular Sturm-Liouville system. Okay. When you are working on the problems for the Laplace wave equation or some other equation, for the equations when you are working on the circular domains, for example cylindrical coordinates, polar coordinates, you may end up getting let us say legendary equation, that is not regular Sturm-Liouville problem. So, that is singular Sturm-Liouville system. So, that is what you get. Okay. So, here mostly if you are working in the if you are working on the Cartesian coordinate system, you will always extract regular Sturm-Liouville problem. So, you have this problem, ordinary differential equation x of x minus lambda is the arbitrary number. So, this is a parameter x of x equal to 0 in the domain x is a to b, and x at a equal to 0, x at b equal to 0. So, this is your Sturm-Liouville problem, regular Sturm-Liouville problem. So, regular type. Okay. Okay. So, you know how to find eigenvalues and eigenvectors. Eigenvectors are all those for those values of lambda for which you have non-zero solutions satisfying these boundary conditions, boundary data, they are eigenfunctions and corresponding lambda values are eigenvalues. So, you find these eigenvalues and eigenfunctions, and then you corresponding to those eigenvalues you come here for pick up this problem, and those eigenvalues you have you can solve this second order equation and get the solution. And once you know this t and x of x, you go and substitute into this x and t, that will give you a solution, kind of solution with some constants. Okay. So, we will see that. So, first get the eigenvalues and eigenfunctions here. So, because we have done earlier, so eigenvalues and eigenfunctions. So, because I have done earlier, so I am just giving you directly. So, here 30 already. So, we can give you directly eigenvalues and eigenfunctions. So, anyway, so maybe because of time, so we cannot finish in this video. So, we will have we will try to find the eigenvalues and eigenfunctions, and once you get these eigenvalues and eigenfunctions, so you will see that you will have lambda n's you can get, and you have some call this some fn. So, eigenvalues, what did I use? We use phi n's. Okay. So, we have phi n f x, this is what we used. So, try to get these eigenvalues and eigenfunctions. Now, you substitute these lambda n's into this corresponding to, if you put it in this ODE, we will try to get your Tn of x, Tn of t's for each n. Okay. Discrete number of eigenvalues you will get discrete number of eigenfunctions you will get, okay, as your xn of x. Eigenfunctions are solutions, you will get these are your solutions. Okay. Let us call this only xn of x as eigenfunctions. Okay. Here Tn of t, they are corresponding solutions of other ODE which we have here. So, because for these are non-zero eigenvalues, their product for each n you have xn of x, Tn of t which is non-zero, which is a solution, because xn of x is non-zero and correspondingly you have Tn of t is also non-zero if you solve it. Okay. So, this solution, this is each is a solution for each n, this is a solution, okay. And then because n is a discrete, you make a sum, maybe n is maybe sometimes 0 to infinity or 1 to infinity, whatever, okay. Let us say from 0 to infinity on a finite sum. Let us not write here because we have not seen what are eigenvalues. So, you make a sum over the discrete index n x n x t n of t. This sum you call it u of x t as, okay, this you call it, this is the general solution. This is the general solution because this, if this is a, for each n this is a product is a solution, any constant C n is also a solution, okay, or maybe that constant. So, these arbitrary constants may be involved for each n inside here. So, you have arbitrary constant inside here, okay. For each n you have arbitrary constant, their sum, actually one can show that the sum is uniformly convergent, so that you can differentiate term by term. If you differentiate ux, if you want, you simply differentiate term by term, that is how you can get ux, uxx, all that, okay. So, finite sum, if it is a finite sum, actually you can differentiate because all are differentiable function, you put it into the wave equation and try to, is actually satisfying because each term is satisfying the wave equation. The linear superposition of finite terms is also a solution of the wave equation because it is a linear equation. You are using here superposition principles. These are all the solutions, you are making a superposition, sum of finite number of them, okay, are also solution. But if you take this infinite sum, the sum infinite, one can actually show that, but we do not show here, one can actually show that this series is uniformly convergent in both the variables x and t. That means you just imagine that uniformly convergent series means you simply can do term by term differentiation, term by term integration, okay. Basically what we need, term by term differentiation. So, it is uniformly convergent, that means the finite sum, that infinite sum, it makes sense, and it actually you can, if you want the derivative of that full sum is actually is equal to that sum of, you just do term by term differentiation you can do, and finally when you substitute, that also satisfies wave equation. So, if you make this superposition, okay, you assume that this is a solution because it is uniformly convergent, you can do that is a solution. You look for solution in this form. So far we have not used initial data, okay. So, once you see that this is the solution that satisfies the wave equation and the boundary data so far. Now, on this general solution you apply the initial data and get the arbitrary constants involved in this Tn, that means it is involved here, okay. That is where we use the dot product of these eigenfunctions. So, the dot product of the eigenfunctions you can use here, phi n phi m, okay, phi n phi m, this dot product you have to use. So, make use of that, we can get those values of the arbitrary constant involved. Once you know those arbitrary constants, you know that is the final solution. This is what we will see in the next video, okay. We will continue from here, we will try to get the eigenvalues and eigenfunctions, and we will try to get this Tn of x for each discrete value of n, and we will try to make the superposition and finally apply the initial conditions and get the arbitrary constants. Finally, that will be the solution of your initial boundary value problem in the finite domain, okay. Finite string, if you want to know the vibration of the string with the initial displacement and initial velocity of the string is known, and with the boundaries are fixed, this you can find the displacement of the string for all times, okay, from this solution. This is what we will see in the next video. Thank you very much.